So here's the result we found, that the energy levels that are allowed are simply Planck's constant squared over 8mL squared times n squared, where n must be an integer, 1, 2, 3. Here we have those energy levels plotted for a well that is 100 picometers wide, or in other words, 10 to the negative 10 meters wide. Notice only these discrete energy levels are allowed. All of these possible energies in between are not available to the electron, because we can't get a standing wave at those places. Now we can imagine that an electron begins and normally exists in this lowest energy level. But it's possible that an electron can jump up from the lowest energy level up to one of the higher energy levels. But it can only do that if it jumps from one allowed energy level to another. It can't, for example, jump to here, which is in between allowed energy levels. Once it reaches a higher energy level, it can drop back down, but once again, it must drop to one of the allowed energy levels. So it can drop all the way from the fourth energy level to the first, it can drop from the fourth to the third, and from the third on to the first, or it can drop from the fourth down to the second, and from the second on to the first. It cannot, however, drop to some intermediate state where there is no energy level. That simply does not happen. Now, in order to make a jump like this, we have to add or take away energy. And the amount of energy that we add or take away is simply equal to the difference in energy between those two energy levels. The energy level of the high part minus the energy level of the low one. If we want it to bump up, we have to add that energy. If we want it to drop down, we have to take away that energy. Now you may ask, how do we add that energy? The most natural way is with a photon, a particle of light. So if a confined electron absorbs a photon, the energy of that photon has to equal the energy difference, because it has to be just the right amount of energy for the electron to take that energy and jump from the lower energy level up to the higher energy level. That means that Planck's constant times the frequency has to equal that change in energy. The same is true for a photon that's emitted when the confined electron drops down from a higher to a lower energy level. The energy, h times the frequency of that photon, will equal the energy difference between the two states. So back here, we send a photon in to bump it up to that energy level, but it must have the right energy to make the jump. Here, we would get a photon out, one very energetic photon here, two smaller ones here, and a moderate-sized one, moderate energy here, and a very low energy here. But in either case, every time the electron went through a jump, I would get a photon whose energy exactly matched the energy difference between the two energy levels that the electron moved between. A brief aside, to say that the energy is exactly this energy difference is actually a little bit too strong. Each of these upper energy levels gets blurred a little bit because the electron doesn't exist there forever. And you remember the uncertainty principle has a version that says delta E, delta T is greater than or equal to Planck's constant over 2 pi over 2. So in other words, if it exists in one of these energy levels for only a very short period of time, which it does, there will be a little bit of blurring in the energy. So these aren't quite single lines, but they are very narrow. Just a very slight range of energies are allowed.